Imagine the densest object in the universe that isn't a black hole. For decades, we thought we knew the answer. The neutron star, a cosmic relic so compressed that a single sugar cube of its matter would weigh billions of tons here on Earth. But what if there's something even stranger out there? Something that pushes the very boundaries of matter, denser than atomic nuclei, stable in ways we never fully expected. This is the tantalizing, unsolved mystery of the strange quark star, a hypothetical object that could completely reshape our understanding of the most extreme corners of the cosmos. The idea of a strange quark star isn't just a fun thought experiment. It's a frontier of astrophysics. It challenges our fundamental understanding of how matter behaves under truly unimaginable pressures and densities conditions far beyond anything we can recreate in a laboratory. If these stars exist, they would represent a unique phase of matter, a kind of cosmic quark soup that could be more stable than the protons and neutrons making up everything around us. Proving their existence or their non-existence would unlock secrets about the forces that govern the universe, from the hearts of dying stars to the first moments after the Big Bang. But finding them and definitively identifying them is one of the biggest puzzles facing astronomers today. Let's start with what we know for sure, the incredible neutron star. These objects are born from the catastrophic deaths of massive stars, collapsing under their own gravity during a supernova explosion. The immense pressure crushes protons and electrons together, forming an incredibly dense ball made almost entirely of neutrons. Think of it like squishing Mount Everest down to the size of a golf ball. The protons and neutrons that make up atomic nuclei, which in turn form all the ordinary matter we interact with, are themselves made of even smaller particles called quarks. Specifically, ordinary matter like you and me, and even neutron stars, are made up primarily of what we call up and down quarks. In a neutron star, these up and down quarks are tightly bound within the neutrons, which are then packed together. It's an extreme state of matter, but the neutrons themselves remain intact. But what if you could push even beyond the neutron star? What if the gravity became so intense, the pressure so overwhelming, that even the neutrons themselves started to break down? This is where the idea of quark matter comes in. Instead of discrete neutrons packed together, the individual quarks and gluons, the particles that bind quarks together, could become deconfined. They would no longer be locked inside individual protons and neutrons, but would instead roam freely in a continuous, superdense sea, much like a liquid. This state is sometimes called a quark-gluon plasma, a phase of matter so extreme it's thought to have existed throughout the entire universe just microseconds after the Big Bang. While we can briefly create tiny droplets of this plasma in particle accelerators on Earth, imagining an entire star made of it is a mind-bending concept. Now for the strange twist. In addition to up and down quarks, there's another type of quark called a strange quark. It's heavier than up or down quarks, and it typically doesn't appear in ordinary matter or even in stable neutron stars. But the strange matter hypothesis proposes that under the incredible pressures found deep within a neutron star, it might actually become energetically favorable for some up and down quarks to transform into strange quarks. In fact, theoretical physics suggests that a mixture of roughly equal parts up-down and strange quarks could form a state of matter called strange quark matter that is even more stable than ordinary atomic nuclei or even the neutron matter found in neutron stars. If this hypothesis is true, then a neutron star reaching a certain density threshold could undergo a phase transition, melting into a strange quark star. And here's the kicker. Some theories suggest this strange quark matter could be so stable that a strange star might resist gravitational collapse into a black hole even more effectively than a neutron star, potentially existing at densities that would swallow a normal neutron star whole. So if strange quark stars could exist, how would we find them? This is where the observational challenge truly begins. From a distance, distinguishing a strange quark star from a particularly dense or unusual neutron star is incredibly difficult. Both would appear as incredibly small, extremely dense, compact objects. The key difference would be their precise size and mass relationship. A strange quark star being even denser than a neutron star, would theoretically be smaller for a given mass. Astronomers have identified a few candidate objects over the years that seem to fit this description. For example, a star known as RX J1856.5-3754 is one such fascinating case. Its observed size appears unusually small given its estimated mass, leading some physicists to speculate it might be a strange quark star. But measuring the exact mass and radius of these tiny, distant objects is a monumental task, riddled with uncertainties. A small error in our measurements or assumptions could easily mean we're just looking at a particularly small neutron star, not an exotic new type of object. This leads us to the heart of the scientific debate, where astronomers and physicists find themselves divided. On one side, some researchers are skeptical, arguing that the conditions required for strange matter to form, or for it to be stable, might never truly be met in the universe. They suggest that the current evidence doesn't definitively rule out a very dense, but still conventional, neutron star, and that our theoretical models of extreme matter are still incomplete. On the other side, many physicists find the strange matter hypothesis compelling. They continue to refine their theoretical models, exploring the properties strange quark stars might have and what unique observational signatures they could produce, like unusual cooling rates or magnetic fields. A third group focuses intently on the candidate objects we've found, working to improve measurement techniques and gather more data, hoping to definitively confirm or rule out the strange star explanation. Crucially, as of today, no strange quark star has ever been definitively confirmed to exist. This remains a vibrant, active area of research, fueled by both the tantalizing possibilities and the immense observational challenges. The universe, it seems, is full of surprises. The very existence of strange quark stars remains a profound and exciting mystery, pushing the boundaries of our physics and challenging us to imagine matter in its most extreme forms. It reminds us that even with all we've discovered, there are still fundamental questions about reality that remain unanswered, waiting for the next generation of telescopes and brilliant minds to unravel them. Could there be objects out there, even stranger and denser than we can fully comprehend, hidden just beyond the edge of our current understanding? The hunt for the strange quark star continues, a testament to humanity's unending curiosity about the cosmos. If you enjoyed diving into this cosmic mystery, consider subscribing for more journeys to the edge of space and science.